So let's see. Last class we discussed state space representation of a translational mechanical system, right? So this class we are going to talk about representing an electrical network. Okay? So this is going to be slightly different from the translational system and overall procedure. So you have to pay attention for this one, okay? So the question would be something like this. Find the state space representation if the output is current through resistor. Okay. So its output is defined. Output is current through resistor. If you're given such a thing, we look at the different steps. Step 1, you'll label all the currents in the network. Okay. So if you have something like this, the current flowing through this would be IL of t. The current flowing through this would be IR of t, and the current flowing through this would be, you would represent that by IC of t. All right, and you can say this is node 1. Okay, there is no node 2 here. You realize that, right? This cannot be node 2 because it is just, there is no element there. There is no element. This is not node 2 just because there is it's a corner, because you don't see an element here, right? It is just one. Yeah. Okay. No, there is no element in this. This is not a node. Between nodes, you need an element here, right? There is something here, there is something here, and there is something here. But there is nothing. If you move this here, nothing changes. If you move this element here, nothing changes. It still be the same here. this voltage would be applied to this entire thing. You see that? So you have those currents. The second step is and this is a very important step. Write the derivative equation for all the energy storage elements. Energy storage elements. So your energy storage elements, you have dt is equal to IC and all your energy storage. So energy storage elements are all capacitors and inductors. For the capacitor, your energy equation or energy storage element equation is this: C into dVc over dt is equal to IC. Okay, and this is a direct implication of the Ohm's law applied to capacitor. What is the Ohm's law applied to capacitor? V is equal to what? 1 over C into integration of 0 to 1 I tau, right? Or I t dt, right? Where t is the interval, the tau is that interval. Right. V equal to IR. Right? This is your, so if you move this and differentiate it, you're going to end up with this. You see that? You see that, right? If you move C here, or you integrate on both, you differentiate on both sides, you're going to end up with dVc over dt on the left hand side. C is a constant, and it will be just IC. Okay, and this is simply Ohm's law for the capacitor, for the inductor. Vc is equal to, this is VL. Okay, VL is equal to L into di over dt. This is the direct Ohm's law. Whenever you do this, whenever you do state space representation of a electrical network, identify all the capacitors and all the inductors and write these equations for all of them. That is your starting point. Okay? So, recall, see, this will help you. Why do you write this is, this will help you identify the state variables. What is the, recall general state space representation. What is general state space representation? Recall right. So if you recall, you have x dot is equal to ax plus bu, and y is equal to cx plus du, right? So you see this one here, Rion, x dot, you see these on the left hand side are this x dot. You see that? VC or VC and IL are x's. Got it? This is a derivative, right? X dot is a derivative, state vector. So this VC is one of these state vectors. IL is the other state vector. That is what it will let you identify. Now all you need to do is express this IC in terms of these variables using Kirchhoff's voltage law or current law, and so we'll see how to do that. Okay, you recognize this part as this. You're able to identify that X dot. If I move C and L on the other side, this will just be X dot, the derivative of the state vector. Okay. Y is output is current through the resistor. So you'll see current through the resistor. What is the current through the resistor? IR. We'll see how we can write that. Huh? We'll get to that. Just give me a second. We'll get to that. So step 3. So this implies state variables are Vc of t and IL of t. Okay. IC, applying Kirchhoff's KVL and KCL to nodes and meshes. So the first one is, you can say IC is equal to minus IR plus IL. Okay. So the current flowing, you can see this, right? If you look at node 1, current flowing in would be equal to IR plus IC. The current flowing through current IL is equal to IR plus IC, or IC is equal to minus IR plus IL. You recognize, do you see why we are doing this? You're isolating IC. You don't want IC. Because, see, everything has to be in terms of state variables. Everything has to be in terms of VC, IL. Right? So, IC, we cannot have that. See, this is a constant matrix, this is a constant matrix, this is a constant matrix, this is a constant matrix. So, these cannot be variables. Your X has already been defined as VC and IL. So, what we have done here is, we have an IL and IR, and IR is your output. This is identified as one of the outputs. So you can express it in either state variables or output, IC. So what else do we need to eliminate? IR is recognized as the output. So it's okay to have IR in the state space representation. The next step is to eliminate VL, because VL is not a state variable. Okay. So how do we eliminate? Now think about yourself. How do we eliminate VL? represent VL in terms of either VC, V, VR. Can you do that? So let's say this is VL, right? The voltage at this point is VL of T. If you apply Kirchhoff's voltage law to this mesh, what are you going to get? So step 4, if you apply Kirchhoff's voltage law, not step 4, that is another step. Can you write KVL to mesh 1? You're going to get VL is equal to V minus VR of VR. Correct? You see that? No? If you applied Kirchhoff's voltage law to mesh 1, the input voltage is equal to voltage drop in this minus voltage drop in this. Huh? Uh-huh. No, it would be this, right? No, it would be V is equal to input voltage is equal to the voltage drop in the inductance plus the voltage drop in the resistance, right? But what we want is VL. VL of T is equal to V of T minus VR of T. Got it? So this is the voltage law. Applied voltage is equal to voltage drop. We want VL of T. Now, you can keep V of T as it is because it is an input, right? But what is VR of T? It is IR of T into R. Correct? So now look at it. Now what you have done is, if I rewrite this, what are you going to get? So step 4, rewriting state equations. You have C dVC over dt is equal to minus IR plus IL and L dt is equal to V minus R into IR. Okay. Or C dVC over dt is equal to IR. What is IR? It is minus 1 over R VC. Plus IL and L di or dt is equal to minus VC plus let's keep this as VR. Okay. This is minus V minus VC. If I just remove this, what you're going to get is C plus 1 over C IL minus 1 over L V. This is plus, right? All right, so you're clear up to this point? So here you're clear. This is clear, right? What is IR? So I can move. How do you express IR in terms of voltage? IR in terms of voltage would be, right? It will be VR divided by R, right? VR, you have to realize, see, this voltage is what gets applied to this thing. Huh? Right. So if you look at this, there are two elements here. If you did not have this, if you did not have this element, the voltage, this voltage would be the same for this. Got it? Voltage, when it is applied to in parallel, it doesn't get split. This voltage gets split into this and this. But these two are in parallel. Right? So this voltage is the same as this voltage. If you did not have this element, whatever voltage you're applying here is the same as this and this. The same voltage gets applied to this point and this point. The potential difference is the same. So VR essentially is the same as VC. So I can write IR equal to this, or VC over R equal to IR. Okay. That's what I've done here. So VC over R, I've just moved C here, and the negative sign is as it is. And the IL, again, it's just as it is. The C is moved here. Okay. Similarly, you will see that VR is same as VC. Okay, and L is moved to the denominator on the right hand side. If you notice, why did we do this? You have to understand why we did this. We still want to eliminate IR because it's not a state variable. Everything has to be in a state variable. If you look at these, everything here is a state variable. VC is a state variable, IL is a state variable, V is just an input, VC is a state variable. You see that? The state variables get identified here when you do the energy equations. The state variables have been identified as VC and IL. Okay? So now you're using a combination of Kirchhoff's voltage law and current law to express these in terms of state variables and input. If you have done this, you have your state equations now. What is your state equations? I'm going to erase this part. Your state equations, so what is, you have VC dot IL equal to, what is A? Can you tell me what is A? Negative 1 over RC, 1 over C. So that is, this is the input, right? So you just have negative 1 over L, 0. And you have plus, so you have, it's here. And then you have 0, 1, sorry, 0, 1 over L, and V. Okay, so you can do this. If this makes more sense to you guys, you can do this. This is the input, the control input. So you see, this is your A matrix is this, B matrix is this, U, the control input or the input vector is this, and your state vector is this. Got it? What? All right, so this is X equal to A, X plus B, U. Now your Y would be, Y is what the output we said was the current through the resistor. So current through the resistor is, so what is the current through the resistor? IR. And what is IR? Did we have write an expression for IR? In terms of state input or state vector. In terms of state vector, can you tell me? What is IR in terms of state variables? Look at here. One of them is already here. This is a state variable. So IC is not a state variable, but you can express it as in terms of state variables. What is IC? C. What is IC? Right. You see that? You can also do this. You can just use this. Can you use this? IR. So you have Y, you have IR is equal to 1 over R 0 V dc into IL of t plus 0. Does this make sense? Because this is a state variable. These two have to be the same. If we do that way, we will end up with a derivative. We cannot have a derivative on the right hand side. So this, whatever is, this vector has to be same here, both places, right? So you have, this is your y equal to cx plus du. So this is 0, but this x has to be the same as this x. So your C matrix would be just 1 over R from this. Okay? Y is equal to IR, because that is what that is our output of interest. That is what it says. You know, find a state space if the output is the current through the resistor. Huh? This is the output equation. The resistance to the current. That is what your question is. Why is it resistance through the current?
I mean, I get that.
Mm-hmm.
So if we were to set this up as a different problem,
Mm-hmm.
and our output, we're supposed to find I plus C. So I plus C would be our Y.
Correct. What you're interested in would be Y. What you're trying to measure as the output would be your Y. Okay. What will give you enough information to control your system? If that is the system variable you're trying to understand, now you have developed the equation for that, right? Now you can do math on that and control it. This one? No. This is just Y, right? Y. Look at this. This is not dot. The dot is only here. Okay. So this is how you develop your state equations for a electrical network. Any questions? Any doubts? Huh? So when you do this, now think about replacing these. These are constants, right? These are system properties. So these will be some value, some number. So these matrices are constant matrices. A, B, C, D are constant matrices. You see that? They are system matrices. They are system properties. And since we are dealing with LTI, what is LTI? Linear time invariant. What does time? This is another context of what time invariant is. These matrices do not change for a time invariant system. The A, B, C, D matrices do not change. State variables obviously are going to change based on what input you apply. But those A, B, C, D matrices are not going to change. That is the reason it is called time invariant. Got it? But you can also these matrices can be non-linear, okay, which is the case for aerospace systems. That would be a time variant. That would be another different this thing. But these don't have to be linear. But when you're dealing with transfer functions, your system has to be linear. Although our scope for this course is limited to only linear time invariant systems. Even when we're dealing this, we're not talking about nonlinear systems. But the practical application, when you, as you said, when you go into actual industry, this could be a nonlinear system. This will be a nonlinear system. So you need to know how to deal with it at that point. Okay, and it will be a time varying system. You cannot design a time invariant propulsion system or time invariant rocket. There is no concept like that, right? So you have to learn to deal with time variant systems. All right, and so I think that should be your lecture for today. Let's discuss a little bit about your exam. Your assignment is due today. Yes. So it is chapter 1 and 2, right? You don't have to see. I won't give you a third order any system with 3 masses. No system with 3 masses. No system with 3 loops. Fair enough. So that time you should be able to calculate the determinant. For 2 by 2 matrix, you should be able to calculate the determinant. I don't expect you to calculate determinant or do Kramer's rule for 3 by 3. So no 3 mass systems, no 3 loop systems, just 2. Maximum is 2 loop systems. Fair enough. But you'll have to be ready to apply both voltage law and current law. Make sure you go through partial fraction expansion. A lot of limitation is partial fraction expansion because I think you'll forget what partial fraction expansion is. And one of the questions, a potential question is to find the response of a system. How do you find the response of a system? By the transfer function. Okay? Now, there are 2 steps to this. You first do the input or response in frequency domain. That is just 1 step. It is hardly worth 2 points. You just multiply. If it's a step input, you multiply 1 over S, right? But if you want to do, if I ask you to find a time response, what are you going to do? You have to take the inverse Laplace, and that is when you need to know partial fraction expansion. You will be fine. If I ask you time response, you do the G of S. You do C of S is equal to G of S into R of S. That is the frequency response. You are given, if your system is this, so here let's say your output is what? I R of T, right? So you'll develop something like this. I R of S over V of S is equal to something, some transfer function, some G of S, correct? Now, if I ask you what is the response of this system, what is the time response of the system? If the question is time response, what are you going to do? You're going to do I R of S. The first step is this. Right? If I ask you response, the question would be, what is the time response to a step input, to a ramp input? Right? This would then be, if it's a step input, it would be 1 by S. If it's a ramp input, it would be 1 over S square, something like that, right? This is the frequency response. Now, how do you take the time response of this? You take the inverse Laplace on this. You do an inverse Laplace. Now, if you're doing inverse Laplace, your g of s could be a polynomial, will be a polynomial, right? It would be, in this case, it could be a second degree polynomial. If it's a second degree polynomial, you have to know partial fraction expansion, otherwise you're going to lose points. This itself, see, this is just 2 points worth. You give me the frequency response from a transfer function. But if there are more points allocated, time response, if this is worth 6 points, you have to do the partial fraction expansion, otherwise you're not going to get points. Take the inverse Laplace, and for inverse Laplace, you need partial fraction expansion.
Are we still having extra session?
Huh?
Are we still having an
Extra
extra session?
session? When do you guys have extra session? I think your extra session is today, right? It's today. 1 to 2, I think. No? 9 to 11? Oh, sorry. Huh? It says clearly in your syllabus. It says, yeah, 9 to 11, right? Huh? No, tomorrow, I am not available tomorrow. That's the reason 9 to 11, you guys chose 9 to 11, actually. I did not choose it. Huh? It's not, see, it's 1 hour, extra session is 1 hour, right? So, you can do it 10 to 11. Bob, how about 9 to 10? Huh? Yeah, office hours, you can come to my office.
Yeah, I was just saying, maybe if there might be a time that I'm available, I don't know, 11 to 1 Thursday. I'll just come to your office.
That's better. See, if you have to, we have agreed upon these. There's a mutual agreement, right? Let's try to respect that. If you want an extra session, you should not be asking it today. Yeah. You understand? You should have, I would have given you an extra session at any time. But on the day when homework, your assignment is due, you shouldn't ask extra session. It's not going to help you. There's only one major problem in that. One big problem. One circuit problem, one translational problem, one rotational problem. Everything else is very simple. It's only, although there are many problems there, it's 1 line, 2 line answers. It's just differential equation. If you just practice it, it hardly takes any time. I have made sure your homework is actually not lengthy. I've given just one example for each. You have to be able to do it one example. Otherwise, how are you going to practice? Not trigonometric function. A complex would be what?
Shifting.
Complex variables. Imaginary and complex variables. That's the third one.
Last question. I have a Laplace transfer table from 307. Should we use that?
You can actually, I will be giving you a Laplace transform table. As part of your, this thing, your assignment, your question paper, the Laplace transform table will be at the back. So you will be using those. You will be allowed to use those. Now, MATLAB, how many more guys want to use MATLAB? Okay. Huh? Sure, sure, yeah, absolutely. I mean, all the questions you can answer. In fact, it would not be very helpful for this test to do MATLAB, because they are going to be short questions. They're going to be like, you're probably going to be faster doing it by hand. Only if it's lengthy calculations, that's when you want to use MATLAB. For example, if you're talking about, let's say, like a 6 by 6 matrix, you will be able to do it with hand, and probably much faster if you learn the material. So state variable is how the way you define it is, it is a linear combination of system variables. Okay. So here, this is your, let's say, Z1, and this is your Z2. For an electrical network, the way you identify state variables is by identifying the energy storage elements, the capacitor and the inductor. For the capacitor, you write the differential for a capacitor, you write the differential for the inductor. For the capacitor, you have to write it. The Ohm's law translates to this. This will help you identify the state variable. So this is the state variable here, and this is the state variable here. When you do that, when you do this, right, this is that vector. So this is the differential. Differential means it will give you, this is like VC dot, right? So VC dot means you know what VC is your state variable, and IL dot, IL is state variable.